You know, the world of quantum cryptography is kind of weird. We hear all the time about how this technology can create completely unbreakable locks. But what if, to be sure that lock actually works, you needed another, special quantum key just to check it?
And that, right there, is the big question we're going to tackle. It sounds like a total paradox, right? Kind of like a snake eating its own tail. But as we're about to see, this strange loop might actually be the very foundation for how we secure our communications in the future.
So, to get our heads around this puzzle, we first need to talk about the hero of the story, a technology called quantum key distribution, or QKD. And its promise is, well, nothing short of perfect, unbreakable security.
Now, the really cool thing about QKD, what makes it a total game changer, isn't that it relies on some super complex math problem that a future computer could maybe crack. Nope, its security guarantee comes directly from the fundamental laws of physics themselves.
Think about it this way. It's like the universe itself is your security guard. The no-cloning theorem means a hacker can't just copy-paste a quantum key while it's in transit. And if they even try to look at it, to measure it, the very act of observing it leaves behind a trace. It's basically a cosmic tripwire. Any eavesdropper is caught red-handed.
Okay, so if the physics is rock solid, where's the catch? Well, here's the twist. The problem isn't the quantum part. The problem is proving that the key you just made is secure. And that brings us to a hidden bottleneck that has everything to do with the limits of our regular, classical computers.
You see, the principles are beautiful and elegant, but translating the messy, real-world data from a quantum exchange into a rock-solid mathematical proof of security, oh, that is a total nightmare. It means we have to wrestle with some of the most ridiculously complex computational problems you can imagine. All right, so the tool everyone uses for this job is called semi-definite programming, or SDP. You can think of it as a computational referee. It takes all that messy data from the quantum communication, analyzes it, and spits out a final score, a hard number that tells you exactly how secure your secret key is. It is the absolute final step. You have to do it.
And this is where it all starts to get a little out of hand. Because as our quantum protocols get more and more advanced, using more dimensions, more measurements, or getting so sophisticated you don't even have to trust the hardware, the size of these SDP math problems it blows up exponentially.
Let's just put that into perspective. For a simple protocol, a normal computer can run the proof in a few minutes. No big deal. For a medium-sized one, we're talking hours. But for the advanced next-generation protocols that we're developing right now, the problem becomes totally intractable. We're talking days, weeks, or even longer. Our classical computers they hit a brick wall.
But what if you fought fire with fire? What if, to solve these massive, quantum-sized math problems, you used a different kind of computer? This is where an unlikely ally enters our story, the quantum computer itself.
And here's the crucial difference. As the problem gets bigger, a classical computer solving time, let's call it the turtle, gets exponentially slower. But a quantum computer, the rocket, tackles the problem in a fundamentally different way. Its solving time grows much, much more slowly. For the huge problems we're talking about, this isn't just a little boost. It is a game-changing, provable speedup. And all of this brings us to the really wild part of our story. This totally mind-bending, self-referential idea where quantum technology is actually used to certify itself.
I mean, this quote from the source research just nails it. The question becomes not just how do we protect ourselves from quantum computers, but how can we use quantum computers to make our security even stronger?
So let's just trace this loop. First, two parties, Alice and Bob, they exchange quantum states. Second, you feed their data to a quantum computer, which then solves that enormous SDP problem we talked about. Third, the solution from that quantum computer certifies that the key they generated is secure. You are literally using quantum computation to certify quantum communication. It's a beautiful, self-contained process. Okay, so this whole loop thing is pretty cool, right? But is it just a neat theoretical idea? Or when does this actually start to matter in the real world? When does this become not just a nice-to-have, but an absolute necessity?
Well, this table really lays it all out. Look, for the standard, basic quantum crypto we use today, classical computers are fine. No real advantage to using a quantum one. But for the future of quantum communication, we're talking high-dimensional systems, totally device-independent protocols, or complex quantum networks. Classical analysis isn't just slow. It's literally impossible. For these advanced systems, quantum analysis isn't just advantageous, it is necessary.
But hang on a second. This is the big, obvious question, isn't it? If we need a quantum computer to check our security, how in the world do we know that we can trust the quantum computer itself? I mean, what if it's flawed or buggy or even malicious? It feels like we're right back at that paradox.
And here is the really clever solution that breaks the paradox. It turns out that while finding the right answer to that SDP problem is incredibly hard for a regular computer, just checking if an answer is correct is surprisingly easy. So, you let the quantum computer do all the heavy lifting to find the solution. Then, you use a simple, trusted classical computer to verify its work. If the quantum computer messes up or tries to cheat, the check will just fail. Or, at worst, it will tell you to use a shorter, more conservative key that is still 100% secure. The security is never, ever compromised.
So this brings us back to where we started, but with a whole new perspective. It leaves us with this incredible thought. Are we heading toward a future where security itself is a conversation that only quantum computers can truly have with each other? One where these systems don't just communicate, but they also vouch for one another in a language our classical machines can no longer keep up with. It's a pretty amazing thought. Thanks for tuning in.